Okay, guys. So we talked a little bit more in the abstract during one of the last videos on how to find Norton equivalent circuits for a given linear network. What I want to do now is actually go through an example of how you practically can go finding a Norton equivalent circuit given a particular linear network. So let's actually do an example. So this is for Norton equivalent. Circuit, an example. So suppose that I'm given the following circuit. I want to find the Norton equivalent with respect to terminals A and B. Right. And the circuit looks like the following. We have a voltage source, or I'm sorry, a current source, providing us with 15 amps. It's hooked up to one resistor there, one resistor there, one resistor there, one last resistor down here. And then you see the terminals A and B on this end. This is an 8 ohm resistor. This is a 2 ohm resistor, a 12 ohm resistor, and lastly, a 10 ohm resistor. So the basic idea behind this is this entire network, as we actually look into these terminals, right, notice that it's composed of one current source and 4 resistors. We want to replace it with its Norton equivalent, which consists of a current source, where this is the Norton current that is in parallel with one resistor, and this is the Norton resistor, like this. Right? So our goal is to find, for that given network, to find first the Norton current and secondly that Norton resistance. And the way we're actually going to do it is we're actually going to consider the open circuit with respect to terminals A and B, find the open circuit voltage. Then we're actually going to place a short circuit across the terminals A and B, find the short circuit current. So we're actually going to find the short circuit current. Actually, let's do it the other way. The open circuit voltage and the short circuit current. And we will find that once we actually have this and this, that the Norton current will be that of the short circuit and the Norton resistance will be the open circuit voltage divided by the short circuit current. Right? So it is these two relationships that we will use at the end in order to find the equivalent network right there. Now keep in mind that the results that you obtain by considering the open circuit cannot be applied when you start taking a look at the short circuit. The behavior electrically of each circuit is independent of one another. That's a big mistake that I see students making quite often, so make sure that you're very, very, very well aware of that. So the first part 1, in the solution, is we're actually going to find the open circuit voltage. So I'm going to go ahead and redraw, or actually for me I'm going to just copy this circuit. Right here. And my efforts are going to be geared towards finding the open circuit voltage. Now the open circuit voltage is the voltage between terminals A and B like this. Now keep in mind that because these are just straight wires, that open circuit voltage is the same voltage across the 12 ohm resistor that we actually have there. Right, so I'm going to make a slight modification so that you can actually see it a little better. right? Notice that if I can actually find the voltage drop across that 12 ohm resistor, then I'm good. I found my open circuit voltage. On top of that, if you actually take a critical look at the circuit that we actually have here, is we have a current source where the current itself is actually entering into a junction here, right? Part of the current is going to split off down this branch. The other part is going to split off this way, go through those resistors like this, and then they're going to join back in here. What we actually have here is a classic current divider. Like, you cannot get almost an easier current divider here. So we're actually going to use current division in order to find the current I that's actually flowing through this top branch. And if I can find the current I that flows through that top branch, I can use Ohm's law across the 12 ohm resistor and get that open circuit voltage. So that's the strategy. So here, one of the things that I can say is, by current division, the current I, right, is 1 over the resistance of the branch where the current exists, divided by 1 over the equivalent resistance of the entire network times the current of the source, right? Keep in mind that the resistance of the branch is the series resistance of all 3 of those resistors put together. So over here, that is 1 over 2 ohms plus 12 ohms plus 10 ohms, right? And 1 over the equivalent of that, well, it's 1 over that branch plus 1 over that branch. So we have 1 over 8 ohms plus 1 over 2 plus 12 plus 10 is 24. So this is 1 over 24 ohms times the current that's flowing into the junction. That is the 15 amps that we have there. So I'm going to multiply this by 15 amps. I don't want you to get the idea that I'm dividing by that, so let me really make sure that you can see that. And let's actually crank this through the calculator. I can't do this in my head. I would hate to try to simplify it too. So 1 divided by 24 times 15 divided by 1 divided by 8 plus 1 divided by 24. This gives us a grand total of 3.75 amps. So we now know how much current is actually traveling through this top branch, which also includes that 12 ohm resistor. This also means that my open circuit voltage, since I had this in green, is the current that flows through it times that 12 ohm resistance. This is 3.75 amps times 12 ohms. Let's crank this out. So 3.75 times 12, that is 45. Oh, what a nice number. So 45 volts is our open circuit voltage. So that's one of the pieces of the puzzle. In fact, this is important enough to box because we're going to use it here in a second. Now, that was for part 1. For part 2, right, we found the open circuit voltage. Here we actually want to find the short circuit current. So I'm going to go ahead and once again redraw my entire circuit. For me, that means I'm going to copy and paste this. So let's copy this and let's paste it down here like this. And the critical part is I'm actually going to place a wire across the terminals A and B. And there's going to be a certain amount of current called a short circuit current that's actually going to flow through the outside of that. Now, notice that one of the things that we do have here, hopefully you can actually see this, is this short circuit, right, is in parallel with this 12 ohm resistor, right? If you place a short circuit in parallel with a 12 ohm resistor, it really is as if this 12 ohm resistor weren't there at all, right? So the circuit that we're actually dealing with, right, consists of my 15 amp current source. The 8 ohm resistor is still there. So is the 2 ohm resistor on the top. We also have our 10 ohm resistor on the bottom, like so. And then the circuit's complete, and the current that we're looking for, just drawing it out neatly, is the current that's flowing through that branch. Hopefully you recognize that this is an even simpler current divider than the one we had previously, right? So here we actually have this branch where we're trying to find the current. There's a second branch right there. This 15 amps, as it starts flowing into that node, part of it splits off into one branch, the other one splits off into the other one. So once again, we can use current division. So by current division, the short circuit current is 1 over the resistance of the branch where we're looking for the current. This is the 2 ohm plus the 10 ohm resistors added in series, right? Divided by 1 over the equivalent resistance of the entire network. So that's 1 over the 8 ohm resistor here, plus 1 over 2 plus 10 is 12 ohm resistance. So this is 12 ohms, and that's for this top part, times the current that's going into the junction that's being split. That's this 15 amp current. Let's go to our calculator to calculate this out. So we have 1 divided by 12 times 15, whole thing divided by 1 divided by 8, plus 1 divided by 12. And this also turns out to be a very nice number. This is 6 amps. So this is important. Let's box this as well. It's so nice to have this modern technology. I would hate to have to simplify this by hand. But our conclusion, really, so far, is that the open circuit voltage we found to be 45 volts. Our short circuit current turned out to be 6 amps, which means that the Norton current, which is equal to the short circuit current, should be 6 amps. And the Norton resistance, which is the ratio of the open circuit voltage to the short circuit current, is the 45 volts divided by the 6 amps. And if you, again, use your calculator to carry out this operation, this is 7.5 ohms. Right? These results are important enough to box as well. Let's actually go back up to our Norton equivalent. This Norton current should be 6 amps. The resistor that will lead you to the equivalent network has a value of 7.5 ohms, and it is this entire thing that consists of our solution. So this entire network, even though it's relatively large, you can actually replace with a much simpler network that consists only of a current source that's in parallel with a single resistor. Right? And that, again, completes our solution.